Thanks for coming. I've observed, especially at my last presentation, that my team tends to ignore me when I'm presenting. So it's good that at least a little bit more people came today. Today we're going to talk about this paper, U-turn on double descent, rethinking parameter counting and statistical learning. So because this is a third order modification, what is expected from you is to know the classical U-turn, is to know Belkin modifications of that, and only then this comes as a rebuttal to modifications. So as you all know, just a refresher for you, when in classical learning, we have a phenomenon called overfitting, and that's been there for at least 50, 70 years maybe. And overfitting is when you have more parameters than the data, or you have a lot of parameters. The simplest example of overfitting is that they give in textbooks is when the data is memorized by the model, and only when your input coincides with the memorized data, then the label is returned. Otherwise, it's a random label, and then you don't generalize. But the version of overfitting that is studied by statisticians more than with the loss function that I just described, 0, 1. And the version of overfitting that this paper is talking about is based on L2, based on mean squared error. So this is from one of this is a refresher for those who forgot what mean square is, mean squared error is, and who forgot about bias variance decomposition. So there is this thing called bias variance trade-off, but we will talk about bias variance decomposition. So if we have an estimate and we have truth, we compute this expression on the board, which you see, computes mean squared error, right? You subtract, square, and then take an expectation over all possible values. So this error is what we use when we train the model. This error is what we use when we talk about the accuracy of the model. And turns out that, like with any metric that is just a single number assessing complex phenomenon, there are multiple things going on under the hood when you're looking at this one number. And we can see this by decomposing this error, taking the square, opening up, regrouping, taking expectations, standard tricks, multiply by 1 or add and subtract. That's all mathematicians do, right? They either multiply by 1 or add 0. That's what this is. Once we do that and regroup again, we get this expression. The first one is expected error of your estimator minus the true error squared. This one is called bias. It's shifted, is the shift of your estimate. This is expected error. So you have an estimator, neural network, decision tree, or whatever, some model that estimates a number. And in the limit of the data, it will give you a number. But this number will not necessarily be correct, right? There could be a shift, like this is in the limit of the data, your estimator will converge on this number. But this bias or shift, don't confuse with the ethical bias and other stuff. It's just a shift. No emotional kind of value attached to the word bias in statistics. Yeah, in other languages, it's actually called shift, shifted from the value. So there will be a shift, but there also will be a spread. And so your error, your mean squared error, consists of two metrics, two numbers. One is the bias. It's how wrong you are in terms of, if you've given all the data, where the center of mass will be relative to the actual target, versus the variance. the mean squared error conflates both of those numbers and puts them together. When you're starting your training here, so your total error is the mean squared error that I presented. And what statisticians observed when training statisticians, machine learners, everyone until that neural network deep learning revolution, and paper by Belkin, is that at this, well, this is different. At this, if you take a small model with few parameters, the error will be high because the model is unable to capture the regularities in the data. We call it underfitting, just the word. When you grow the model too large, when the number of parameters is larger or significantly larger than the number of samples in the data, then again, your error is high. And traditionally, we call it overfitting. You have too many parameters, et cetera, et cetera. And it was conventional wisdom reflected, now I'm speaking a little bit from the paper as well, reflected in many metrics, in many model selection metrics. If you have two models, which one should you prefer? And the preference was go to a model that gives you a good result, which is not displayed here, and lower lower number of parameters. So, for example, if you have log likelihood of your model with respect to the data model, and you want to select a model with larger log likelihood, like with a better fit, then surprisingly or not surprisingly, larger model, the model with more parameters, will always give you better likelihood. For example, if you're trying to select K in the K-means algorithm by looking at the model likelihood, it will tell you to select as many clusters as there are points there. It's just you continuously getting a better fit. So what people came up with is different versions of regularizers, and I'm faking it because I don't remember the exact value, but approximately, basically, n is the number of parameters in the model m, and subtracted. It should be subtraction. The more parameters, the more penalty you're adding, and I'm trying to recreate here Schwartz Bayesian information criterion, but I'm missing normalization factor, etc. Just talking about conventional wisdom. In the beginning, your bias is high, your variance is low. In the end, your bias is low, but your variance is high. So that's where this paper comes in. And I will be jumping back and forth with this paper. Well, not. Let me see. Let's try. I'm unable to zoom on the aspect ratio. The aspect ratio will be as it is. Sorry. But okay. So in nice. Misha Belkin and co-authors, they showed, remember this axis is the algorithm complexity axis, or model complexity. Few parameters, many parameters. Classical U shape curve. It was like that. And people, the story by Belkin et al. Is or at least my reading of this story is that people just didn't look past this point because we didn't have enough computational resources. We didn't have a reason to go and work with models with large sets of parameters. They did, and what they showed is you keep training a model with larger and larger set of parameters as you go along this axis, and you observe the classical statistical U-shaped curve that the model is underfit right here, then the model starts overfitting, and then usually we just stop. The model is getting too large, we're overfitting anyways. But they continued and then observed that the model was getting better and better and better again. And this is the first descent, and this is the second descent, and this curve is called double descent curve. Large hit in computer science and machine learning because this is what was not expected. It was kind of expected in the following sense. In 2015, the whole field was raving about how come those large models trained by local minimum search even learn. And empirically, as it happens often, empirically, a lot of results were obtained that we had no theory for. First of all, the theory would tell us the larger models overfit. That wasn't the case. How come? We could just crank up the models size and then turn on drop out. Yeah, but then people found out that you don't even need drop out. Just take a large enough model and it works. So that's where I think Belkin et al. Started to think about this. It's it's clearly truth. It's happening. How does how does the theory explains that? The local minima stories were that's just a separate thing. Let's just focus on this. So back to the paper. I think the paper is very well crafted. Even the abstract is pleasure to read. Even though some of I wish I could write this conventional statistical wisdom. I would be struggling for days trying to formulate or find references where this double descent curve or just the regular U-shaped curve comes from. And they're like, statistical wisdom, easy, reads well and doesn't explain anything. But yes, so U-shaped curve is there, second descent is there. Then a surprise published by the same group, Belkin et al., was that okay, deep learning is magic, right? It's alchemy, etc., etc. It's okay that weird stuff is happening there. We just discovered it. But they show that if you take trees, if you take linear regression and what was this word, boosting models, you also can demonstrate that there is a phenomenon of double descent there. Those models, linear regression, etc., have been studied for hundreds of years, well, 100 at least, and nobody saw that, so it was very surprising. That's where this paper comes in. What they do in this paper, they only look at classical models for which double descent phenomenon learning was demonstrated. And in this paper, they explain that in a sense, this is not a real but apparent phenomenon because of our interpretation of model parameters. They show that there are two classes of parameters in the double descent curve. That's how they, in this figure, that's how they distinguish them. And in both of those classes of parameters for those models, if you consider them separately, you still have classical statistics that hold, classical statistics, conventional wisdom that holds. But when you conflate them together, then you get this double descent curve. without understanding that, hey, this spike over here is when you're starting manipulating that second class of parameters. They convincingly demonstrate that in a lot of empirical results, besides the theory, where they can shift the spike anywhere they want, or they can smooth the spike by simultaneously moving kind of coordinate descent in one class of parameters versus other class of parameters. Moreover, this is all about those classical models: linear regression, trees, and boosted trees, random forests. So they demonstrate. Oh, they found another thing. They found another way to represent parameters, which they call effective number of parameters. And they demonstrate that in this space, in the effective number of parameters, no double descent phenomenon is observed. It's all classical, that how it should be. So let's look at the paper now, like the actual results, line by line.
It's curious that this paper is as late as it was. I thought this was an earlier paper given. I mean, there's so much literature on overparametrization and neural collapse and stuff.
Yes. Well,
And this is a NeurIPS paper. Got it. I'm also surprised at that.
it's one of the notable papers. It's no, but like it's not widely known what they do. Well, like even the double descent paper it's any surprising result will be not noted. Well, and this result is surprising.
It's not though. It's overparametrization is old. It's at least 7 years old, 8 years old. Maybe.
Well, but that's Belkin's result. Yeah, and the team. This one explains that the results obtained on classical models do not contradict conventional statistical wisdom. They fall within the existing theories very nicely. And like literally there is no double descent phenomenon in those. Well, there is, but it's just because like they explain it why it happens, and yet they don't touch the deep learning part of that. Although we can and we should talk about what is happening with deep learning. So what they're saying, if you consider separately, somehow there is this L curve and U curve, okay, and they stick to the convex. Oh, both of them convex, and that means they're within the classical realm. But the classical statistics would only talk about U curve, right? I showed you in the beginning of the slide. It's you have underfitting when the total least squares error is large. And you have overfitting when the total least squares is again large, but because of the wrongness in another parameter of this decomposition, when MSE is decomposed into parts, bias and variance. Well, anyways, L curve is still surprising for me. What that does L curve mean is you keep adding parameters of a certain sort. I will explain what they are, and it doesn't hurt. So you have a model with two kinds of parameters, and one kind of parameters hurts your performance. The more of those parameters you have, the worse it starts performing, going up here, the curve here. The other kind is like, yeah, you will saturate, but you'll be okay. So that's kind of. They are also demonstrating, by recalling a bunch of literature, by showing their results. But Brad, you will enjoy the theorem because I think the theorem must be known already. But anyways, the correspondence between.
So far, I mean, I didn't read this paper, so I don't know. But so far, it just seems like they're like overparametrization is the thing well studied in deep learning. Let's just study it in other models, and then.
No, they didn't do that. Somebody else done.
Somebody else did it. Okay.
Belkin, who is talking about overparametrization, studied that. And they're saying that their conclusions are wrong, and here's why, and they demonstrating that. So there is no overparametrization phenomenon. There is no, basically they're saying there is no real double descent curve in classical models that has been studied.
Within subsets of the parameters, is what you're saying. there's no double descent.
Okay, since you haven't read the paper, let's wait
Yeah.
until I actually show the
Yeah.
results, because it's like, there's no sentence here. Okay, overparametrization, yeah, they're showing, so here's the, how to, let me see if, something will work. Slightly larger view. Yeah, okay. Originally, double descent in trees was considered in the following way. We take one tree, we'll build one tree by using increasing number of leaves in the tree, decision tree. So you decide to randomly split on a value. So you have n features, each feature, you decide the value and you split, you go to one branch to the left of this value, higher or lower, you go to the right of this branch. And number of trees, number of leaves in trees is limited by the number of features. Basically, once each feature gets on a leaf, that's it, you need larger dimension. Double descent curve is observed when this paper, multi-author, but Belkin is the first, that's the B. Only looks at this leftmost combined parameter when you have everything together. What they do is once one tree is constructed, they just start constructing another tree. And they're kind of effectively, they do ensemble, although they call it a decision tree because they don't do any other boosting and the tricks that random forest is doing. So it's kind of a special random forest, but they don't call it that way in this original paper. So what, and you see that with the random trees, as the number of parameters is increasing, you are experiencing double descent. There is a spike in performance, it becomes worse at a certain number of parameters, then you keep adding the parameters that is growing the trees, and the spike in performance improves. If you separate, like if you fix number of trees that you use, this is P of n's ensemble, I guess, then you see classical convex curve, U shape, they call it, but yeah, with number of leaves in the tree, performance decreases. Up is bad, low is good. Then they do reverse. They fix the number of leaves and they vary the parameters. Parameter number grows, but they show that it's still convex, like in that figure. The red plot. And they separate, I was reading it in the monochrome, so I didn't know there are colors. It was still accessible. Okay. When they separate this, they show that there is no double descent in each of them. So in each of them separately, it's only when you combine the parameters. And so here they're saying, look at this figure. We can get the spike shifted basically by knowing this, that number of trees is separate from the number of leaves. The number of the spike shifts depending on the number of trees. Let's go to gradient boosting. That's your random forest practically. You have the same phenomenon, double descent, as shown in the original paper in Belkin et al. Here. and you have the same decomposition on a different lines. But the interesting part, I thought, this one is easy to explain. What are those two classes of parameters? Trees versus leaves in each tree. That's one. But then linear regression. How come that in linear regression you can also observe this phenomenon? And this is tricky because, well, in linear regression you just solve this problem. Y equals x times beta. You're finding this beta. You have y and you have x. You're finding the betas. But wait, x usually is data for us, right? How do you change the size of the data? Pause here. Don't just trust me on this, because look, when we are solving this model, the parameter numbers that we're claiming now is the size of beta. But beta is not an arbitrary thing. Beta depends on our x that is collected. And okay, if number of rows is fixed, those are number of data samples, where do we get more parameters here? When I read this, I was just like, what is going on? Like, how can they? Here's a way around it. Remember how we do kernels? We take two parameters and create a polynomial kernel with three parameters, and etc., etc. So basically, and this is not the idea of the authors of this paper, it's the idea of Belkin et al. There. So what they do, they take this formula, Fourier analysis, right? So cosine theta plus I sine theta. And they use something called random Fourier features. The way they generate those features is they take a random Gaussian vector P multiplied with the data, and that's your angle, and you take real value of this vector in the complex space. So you take the real part of this, not the real value, real part of this you see here. So I assume it's just cosine theta, right? By Weber's formula there. And they do it any number of times they want. So the same feature vector, your x, your data here, is d-dimensional. But from this d-dimensional, by this random Fourier features, you can expand or contract any way you want. This is kind of interesting because you're not adding any information. You're just adding jitters of more and more representations of the same information. Right? That's all normal. Remember the classical solution to linear regression problem? Unique least square solution, pseudo inverse over there. This is unique as long as your n is less than d or equal to d. But as soon as your d, this dimension, or number of parameters, number of betas, becomes large, that is, your number of equations is smaller than the number of parameters, you have multiple solutions. You don't have a unique solution. What Belkin et al. Are doing, they're saying, well, but we only want one solution. And one solution that they obtain is regularized solution. Basically, it's called the minimum norm solution, L2. Take an answer for which L2 norm is minimum, and it is given you by this formula. So then linear regression, everyone knows what linear regression is, has seen it, and cannot be surprised, right? It's a beaten approach and algorithm, and yet double descent that hasn't been observed, or at least hasn't been in the collective subconsciousness of our field before Belkin's paper. linear regression, you create more parameters in a fake way there. And at first, the fit is bad, becoming bad, and then it's becoming good again. Double descent and linear regression.
What is the bottom axis? It's number of parameters.
Number of parameters. That's so you have this X matrix that you multiply by the beta vector, and the size is here, and the size could be, like your Y is fixed. It's the same dimension as the N here, but your betas could be any number. But the trick there is that and I don't know if I can convey it simply. It's a simple linear algebra anyways. The trick is here, right? Once the number of parameters is large, the rank of your model matrix is the minimum of the two sizes. So, I mean, could be less, but it's upper bounded by the minimum of those two sizes. So what they're claiming is that this theorem, that the minimum norm solution here is equivalent to just picking the full rank part of the basis of that P phi matrix. So even though your matrix is all of the is n by phi, where phi is infinitely large, whatever number you want, the right singular vectors of x, or but basically the n of them, the full rank part of it is all that you need to get the minimum norm solution. But it will be a different minimum norm solution for all of those matrices. And here they lost me because they're using some kind of a magic words that I don't understand. Reach, as in enriched. Capacity. So what they're saying, even though those dimensions in Fourier space are fake and the rank is exactly the same, let me just go through my underscore. Increasingly rich basis. So the basis is the same size, but it's tilted and rotated differently the more Fourier features you add. Just kind of like argumentation to me. Look at this top figure. Look at this. So if you just use your data, actual X, your error is higher if you jitter that data with Fourier basis. You don't have any information, but you're still getting a better fit, better least squares fit to the true Y. Does it make sense? Does it make sense that I'm confused?
I follow what they're doing, but.
Yeah. I'm confused. I mean, I exactly follow what they're doing, but like.
Yeah, and all this low rank stuff is like, yeah, I mean, we've been seeing it for ages. Yeah, I don't know.
No, but the part is that they find that this first group of parameters that actually increases the rank of the matrix is like first class citizen, or like one part of parameters that are orthogonal. And once the rank of the matrix is overcome and you keep adding the parameters, then it's a different class of the parameters above the rank. And they prove it on this figure. Yeah, let me just interrupt anyone.
Raise my hand should be polite. Sorry.
Sorry.
Ed, I'm just gonna throw something out there and like let it seep into y'all's minds in case it makes sense. Is it possible? So like if you increase the number of parameters, you're basically the number of solutions to your equation increases from one to many. And then So could it be that like basically,
Not smoothly.
but it does start to increase from, you get multiple solutions to the equation, right?
Yeah.
So like, I'm basically thinking like maybe like, you're increasing. Like you're increasing the number of solutions, which would decrease the distance between any initialization and a solution.
To the line of best fit, because the what is the mean square goes both ways, right? And the line of best fit and from the variance. It's the accuracy is the line of best fit, right? And then it can be below it or above it. So that's what I was thinking too. Is maybe it's like shrinking. Right? So,
Well, you're specifically you're picking there are many solutions. They all will give you the same exact fit. Which solution to take? What you're explaining will be exactly the same. Many solutions they will give you exactly the same sum of squared errors. They're taking a solution with a minimum norm, with an L2 norm that is minimal, and so there is that way they guarantee unique solution all the time.
For linear regression.
For linear regression, just for linear regression.
Okay, so in deep learning, what I'm saying is that basically, like, could it be that like, since you're random, you have some sort of initialization procedure that, like, as you get these multiple solutions that would do pretty good, you're kind of the number of parameters increases the likelihood that you're relatively close to these good solutions. Because you're not imposing the norm constraint on having one unique solution. If you can arrive at any of the.
Yeah. Let's get to deep learning in just a little bit, because what this tells us, the linear regression story especially, is that there is an effective number of parameters versus the actual number of parameters. They quickly jump to the effective number of parameters by observing that all of those models that so far been considered, trees, boosted trees, and linear regression, are statistically smoothers. And they define what a smoother is. They're smoothing models, I forgot what they call it. Okay, smoother, yeah. It is here defined. So splines are smoothers. K-nearest neighbors are smoother. When you're looking at, you have training data around you and you decide the value, it's like interpolation, right? And you decide the value of at a new point that is not in the training set based on a fixed number of fixed function. So this is your training set, classical representation. We're considering just y is just a scalar. It could be anything, but it's just a scalar. Training set, scalar value for y and subvector x, etc. This is a vector because you're considering all the values, all of the training values. And a smoother is a function that, or any of those are this function, such that you have another vector that depends on the input data, and you have a product of that vector with training values of the labels. This vector S, when it is computed independently of y, those are linear models. When its values depend on the y in the training set, those are non-linear models, but they still can do local smoothing. And when you have this local smoothing, then what they talk about here is they can, for any smoother, they can specify effective number of parameters. And effective number of parameters is defined as the sum over the training data of L2 norm squared of this coefficients S computed at all of the training data. And this effective number of parameters is where no double descent phenomenon is observed. effective number of parameters does not increase past the transition threshold. Yes, okay, that's what they're saying. So this peak or the spike on the last graph happens at the dotted transition threshold, and that's when you saturate the effective number of parameters. That's it. The effective number of parameters is fixed for all of those smoothers when they represent that. The interesting bit about it is very quickly running out of time. They're showing different performance. Is this plot? Is that you when you re-represent this plot, or when you re-represent your error as a function of effective number of parameters, then no double descent, basically it's called convex. I don't know what, I didn't catch what breaks here, but it's a convex curve now. The interesting part I didn't quite digest, that they're saying statisticians, when they consider linear regression, especially, or any kind of those problems, they would take, they are, what they're claiming is they're interested in the in-sample performance. Basically, you have a grid for X values, and the grid is fixed. What changes is the Y, which you feed afterwards. In machine learning, we switched to being interested in the out of sample when the grid is different. We train a model here with X varying from 1 to 10, and then we give it another X varying from 10 to 20 or something like that. And statisticians never looked at this problem. They never were interested. That's why they couldn't have observed that double descent curve. Like nobody was really interested when this bias variance trade-off, underfitting, overfitting came into language. Nobody was really interested in out of sample performance in this sense, that your test samples are different than, not just different, but they're located in a different space of the domain. That's kind of their explanation. Once you start putting your test samples in a different space of the domain, both X and Y are changing conceptually, not just the Y. Just imagine this this curve, the classical. Okay, you want to put. You were talking about the fit, right? The fit. Well, but those values are fixed. They're always there. You can change the Y and get another fit, another problem, but those values are fit. But now with machine learning, they're like claiming, okay, now you got the values here and you want to generalize from here to there and stuff like that. So that's an interesting point for me. But I don't want to finish yet because they give very nicely written, very nicely put in context. Some of the parting points are interesting. Yes, so here they're claiming, okay, since Belkin and all paper at PNAS, the field was wondering, wait a second, our like the previous wisdom of 50 years about the U-shaped learning curve, how could we be so wrong? And so with this paper, they explained that they weren't wrong. The classical statistics still holds, it's still there, as long as you distinguish those two classes of parameters. The classical statistics applies in both spaces. Deep learning, they don't, or they can't say anything. They have interesting hypotheses, and of course they're saying that could be fruitful. But here's what I think. Think about linear regression and this minimum norm and the rank of the matrix. So what if there is n that connect that to the lottery ticket hypothesis? There is an implicit space of a neural network, potentially, that implicit rank of a neural network, and you're just adding those other parameters that they don't increase the rank. That is back to your work. We see that's still the gradients, but those additional parameters may help you to regularize everything back to like closer to solution, or something like that. Like the linear regression line gives you the trend, and then you memorize how far away outliers can go. For that, you need more parameters to memorize the outliers, but to have the trend really well. So maybe neural network has some internal regularization mechanisms or rank, where rank is not in linear algebra sense anymore, but some kind of a limited space, regardless of how large it is. Maybe it's determined by its architecture, maybe, but they kind of speculate on that. And then practical implications. Sorry, I read it the last. I should be remembering, but what they're talking about there. Training data. No. Well, the linear algebra or the linear regression result was a surprise for me. Like interesting that it's kind of like augmentation when you fluff your data by representing this differently. You still get better and better results without overfitting. That's all. I think this is a good paper to be aware of. Very interesting results summarizing what we know about the topic, and it's a good sample of good writing. Maybe they're selling well, maybe they're actually writing well, but it's written very smoothly, I would say. But you're just like, okay, yeah. But even when you disagree with them, you're kind of like, yeah, well, that is possible, but thanks for coming. That was my presentation for today, and thanks for watching those people who came online.